Okay, so we are in our last lecture, and today we will finish up on everything that we've done, and you should know at least what a quantum circuit is, and then what a quantum computer is. Okay, so this is lecture 20. So last class we talked about uh, generalized QM laws. Okay. For the most part, at least when we're defining circuits, you'll see that the circuits are kind of operating on 1 or 2 qubit systems at a time. But when you chain them together, it can become a n qubit system, which is much more complicated. Okay? Just as for circuits, AND or OR gates only take 2 variables at a time, but then you can compute much more complicated functions. Right? In the same way, the same thing is going to happen even with quantum circuits, and that's why we looked at generalized quantum mechanics laws that we need for defining quantum computers. And then we looked at, in the same vein, we looked at multi-qubit systems, and then started building circuits. Okay, so today my goal is to kind of more examples of circuits. Okay, and also to get some familiarity with calculating with these things. As I said, or as physicists have said, you can't really argue with nature. We just have to calculate. Okay, 1 second. Okay, so we just have to calculate stuff. And the most important tool for calculating or computing or figuring out what a quantum algorithm or quantum circuit will do is linearity. Okay? For whatever reason, unlike everything else we've seen before, nature respects linearity. Okay, and we'll see how this helps us figure out how states transform and how computation proceeds. And finally, we will be able to define our model of quantum circuits. And then if we have time, I will talk about quantum advantage. The last part, hopefully I'll say some of the most prominent results and, highlight the common pitfalls and how they're phrased in popular media. And then maybe if time permits, I'll do one concrete example. Okay? All right. And before going on, some announcements to keep in mind. First is that, okay, exam 3 is on December 9th, 8 a.m. to 10 a.m. Okay, so make sure you're there. And homework 6 is due December 6th at 10 p.m. Okay, so keep this in mind. So the deadline is different from all of the other deadlines. So this homework is due on Saturday. And as before, you get 100% credit if you make an attempt. The solutions will be released on Saturday. So if you don't submit it, I can't say give you extra time because the solutions will be out. Okay, the solutions will be out so that you can practice. Okay, and I think that's about it. Okay, so let's briefly review some of the important tools that help us figure out, kind of what happens when you run this quantum gates and quantum circuits, right? And we had this notion. Okay. So states in the quantum world are just vectors, okay, in some dimension. Okay. And at least with the simplified view we are taking, which is already enough to get all of the quantum advantages, but the calculations will become much messy if you do it this way in the long run. But all of the vectors have just real valued entries. If you really want to dig deep into quantum mechanics and quantum computing, you have to allow complex numbers, but that's a separate story. Okay. And we write quantum in, if you're a quantum undergrad, meaning someone who knows quantum computing or quantum mechanics, from now on, whenever you think of vectors, you should think of writing them in this ket notation. Okay, it's kind of a weird notation if you see it the first time, but it makes many things much nicer when working with states and quantum laws. Okay, essentially, it's just a vector which has d coordinates. And we can think of it as alpha 1 times 1, like the first basis vector, alpha 2 times the second basis vector, and so on. Okay? All right. And the other thing that we talked about was dot products. Given two vectors, u comma v, we define the dot product. In quantum notation, you write it with this flipped ket, which is called a bra. It's like, bracket. So u slash v is u1 v1 plus u2 v2 plus so on all the way up to ud v2. Okay? And this helps us calculate lengths of projections, and hence what are the probabilities of different measurement outcomes when you apply various measurement devices, right? So for example, if I have two vectors, u and v, then the length of this projection, so if v is a unit vector, let's say u comma v are unit vectors, then the length of the projection is the dot product. Okay. The length squared is the dot product squared, and this is, this helps us massively in computing various things. Okay. Any questions so far? And the other thing to keep in mind is, going with this, a k-qubit system is like a vector in 2 to the k dimensions. Okay. So if I have 1 qubit, I have 2 entries, alpha and beta. If I have 2 qubits, then I have 4 entries. If I have 3, I have 8, and so on. Okay? All right. And this is kind of a review of what we were doing, and then we were looking at different circuits. And today we are going to look at some more important circuits. So let's look at a famous example. It's famous in physics. It kind of came out from there. So let's talk about that. So what is the circuit? It's a 2-qubit circuit. So it has 2 qubits, 2 photons, and the circuit just takes the first qubit, passes it through the Hadamard gate, and that's it. Okay? The second qubit is not being touched. And you get 2 other photons, right? So this is a circuit, and you might wonder, okay, what is this circuit doing? So let's see what happens, right? So imagine my input state is 0, 0. So both of my qubits are in state 0 and 0, and I want to figure out what happens to the outcome. What do I end up in here? Okay? So how can I do this? I mean, there's some intuitive guesses you can do. Most of the time they work. Some cases, some important cases, when the things are entangled and so on, you have to be extra careful. But until then, at least, we can make some guess, right? So the first qubit is going through the Hadamard gate, where the second one, nothing is happening to it, right? So for example, what would happen here? Any guesses? Let's see. So if I just send in a single qubit, okay, so which is in state 0 through the Hadamard gate, what would I get? I would get plus, right? That's the definition of Hadamard gate. What does Hadamard gate do? It kind of, reflects about the 22.5 degree angle. So if I'm 0, I get transformed to plus. Okay? So if it was only a single one, this is what I would get. Okay? So here I have 2 qubits. So what should happen? Any guesses? Yeah, exactly. That's exactly what happens. I would get 0, 0 plus 1 over square root 2 times 1, 0. Okay? All right? Any questions? This is simple enough, right? Okay? And you can actually derive these things much more formulaically, but we're not going to do that for every possible instance. We saw this, we can think of it as a matrix. We can think of it by figuring out what happens for each of the basis vectors and then writing down the full transformation and so on. Okay? All right. So this particular circuit, the way it transforms 0, 0 is it gives out 0, 0 over root 2, 1, 0 over root 2. Okay? And again, this is very qualitative, so it is helpful only when you're dealing with single qubit systems or 2 qubit systems and you're trying to gain some intuition. It won't work when you scale things up or chain things. But you can think of this 0, 0 as basically saying, with amplitude 1, first qubit is in state 0, second qubit is in state 0. Okay? Right? And it might help you to do the calculation where you might say, okay, now if I apply the Hadamard gate to the first qubit, what would I get? I would get, with amplitude 1, first qubit is in plus, second qubit is in 0. Okay? But plus itself can be broken up, and that's what we essentially did. Okay? All right. So let's do a slightly more complicated example, and then we'll put these two things together. It's, in reality, it's actually less complicated than Hadamard, at least in terms of definition. But physically implementing it, as I will tell you, is turned out to be very challenging experimentally. This is our example phi, and this is the C0 gate. Okay. So there's a classical version of the C0 gate, which is, it's a function which takes 2 bits. If you have done an architecture class, you might have seen this before. It takes 2 bits as input. Actually, let me not write it this way. And it's typically denoted this way. C0 or control not. So it takes 2 bits as input, and the first bit always goes straight through. The first bit is never affected. Okay? And the second bit gets XORed. Meaning, if the first bit is a 0, the second bit also doesn't get changed. But if the first bit is a 1, then the second bit gets negated. That's why it's called a control not, right? So the first bit is controlling whether or not the second bit is getting negated. Okay? So technically, you might hear the term, some say like, okay, this is the control bit. So it tells you whether or not the second bit is going to be negated or not. Okay, this is the classical version so far. I take 2 bits. If I send in 0, 0, I'll get 0, 0. If I send in 0, 1, I'll get 0, 1, and so on and so forth. Okay? Now, I can ask for a quantum version of this. What do I mean by that? Okay, so I want to send in 2 photons, and I should get 2 photons again. Okay? And the desired behavior of the quantum C0 is kind of the same thing that we did for NOT. We want to do what the usual classical gate would do on the basis states, but then we need to extend it by linearity to every possible superposition. Okay? So, in particular, I need my QC0 of 0, 0 to become, what should this be? Just 0, 0, QC0 of 0, 1 should be 0, 1, right? QC0 of 1, 0 should be 1, 1, right? So the C0 gate classically would check the first bit, and depending on it, negate the second bit. The first bit is a 1 here, so the second bit gets negated. Would be 1, 0. Okay? All right. So once again, we have a gate where we know what happens on a basis. So we know exactly what the gate is supposed to do on all possible superpositions by linearity. As I said, and I'm trying to emphasize as much as I can, linearity is kind of a weird constraint, but it tells you what happens not just on these 4 states, but what the quantum gate is going to do on any possible superposition, right? So QC0 of, let's say I have a linear combination like this, would be alpha 0, 0 times 0, 0, okay, plus alpha 1 0 times 1 1 plus alpha 0 1 times 0 1 plus alpha 1 1 times 1 0. Okay. So this is the definition of the quantum CNOT gate. Okay. And just as before, we can once again write down a matrix for it. Right? So we did something similar last time. So we wrote down the input, output, and then tried to figure out what the matrix was. So we can do that again here. So alpha 0 0, alpha 1 0, alpha 0 1, alpha 1 0 should become see, so this is alpha 0 0, this is 1 0, and sorry. Okay. So basically, it just kind of swaps these two entries. That's it. Right? Kind of a simple enough operation. It's a linear transformation which takes a vector with 4 coordinates, and in this particular ordering swaps the second and fourth entries. Okay? And we can write down the matrix from that. Sometimes you can guess it. Once you guess it, you can write down exactly what it's supposed to be. So the first coordinate is not changing, so this is what it should be. And the third one is not changing, so the third one should also just be 0 0 1 0. And the last two things are getting swapped, so I'm just going to write that down. So this is 0 0 0 1 0 0. Okay. You can check this, with some calculations, but essentially I'm swapping these two entries here. Okay. All right. So it's a simple enough operation, almost very close to the quantum NOT gate, except you're only doing one swap, whereas quantum NOT was doing two swaps, right? Okay. But here comes the kicker. To physically realize this gate was very challenging. To implement this gate as an experimental thing took a long time for physicists. Okay. The classical CNOT gate I can build with maybe one or two AND and NOT gates. So it's very easy to implement. It just give me some maybe couple of LEDs or not LEDs chips, and I can do it. Semiconductors, and I can do it, right? Whereas the quantum CNOT gate took a long time, and the first physical realization of a quantum CNOT gate was in 1995. Okay. After almost 10 to 20 years of experimental work, people were able to reliably replicate as an experiment the quantum CNOT gate. Okay. It seems counterintuitive as to why such a simple looking operation should be tricky, but as I said, the main novelty is you're not just implementing something on these 4 states. It should extend to all possible superpositions. Okay. If I wanted this behavior, the behavior of the quantum CNOT only on the basis states, that's very easy. But I want it on all possible superpositions, and that's very hard to do experimentally. Now it's a lot easier, but initially it took a long time to build such an experiment. Okay. Any questions about this? Okay. So we'll do a few more examples, and then we'll stop doing examples. The next example is also very important in theoretical physics. Okay. And I'm just, let me call it, let me not give it a name yet. I'm just going to draw the circuit. It's a circuit with 2 qubits as input. Okay, and you're going to get 2 qubits again, right? And I'm just going to chain 2 of the gates that we've discussed. I'm first going to apply the Hadamard gate, and then I'm going to apply the CNOT gate. The first bit as a control. Okay. So this is my circuit. You can once again work through what it does by looking at the operation on each of the basis states, and then maybe write down a matrix. There is also a way to get at the matrix more directly if you're comfortable with tensor algebra. But for us, all of that is not too important for now. But I want to process what this circuit would do on one specific input. And that input is 0, 0. Okay. So let's say this is my input. The first photon is in 0, the second photon is in 0 as well, and I want to know what happens to the output. Okay, so what's the output I get? Okay, and to compute the output, I can go through stages, right? Okay, so imagine I send in these 2 photons through. After applying the first Hadamard gate, I'm in some particular state, right? So what is my state? We kind of already computed that. Where did it go? If I send in 0, 0 to the first Hadamard gate, I would get this particular state, right? So in this evolution, after the first gate, I end up in 0, 0 plus 1 over square root 2, 1, 0. Okay? And then I'm applying the quantum CNOT gate, right? But we also know what the quantum CNOT gate does. We know what it does on the basis vectors. So by linearity, we should know what it does on the whole state. Okay? So what would happen? I should really get 1 over square root 2 times QC naught of 0, 0 plus 1 over square root 2 times QC naught of 1, 0. Okay? But on 0, 0, the QC naught doesn't do anything. It's just 0, 0. On 1, 0, it flips the second bit. So you would get this. Okay? And this is called an EPR pair, named after Einstein, Podolsky, and Rosen, who introduced an experiment involving these sort of qubits. Okay? So the interesting thing here is that you have 2 qubits, right? And the first qubit state in both of them, they are the same. That's 0, 0 versus 1, 1. Okay? And if you've ever heard the term entanglement, then this is the most entangled pair you can have. Okay? So somehow the first qubit state is intrinsically tied to the second qubit state. And this led to some seeming contradictions, which even to this day some physicists debate over. For example, Einstein, Podolsky, and Rosen, they said, okay, I take my 2 qubits, run it through this circuit. Now I get 2 qubits again. I put one on Earth, one on the moon. Okay? And somehow if I measure the first qubit, something happens to the second qubit as well because of the collapse. Okay, that was the contradiction that they were trying to explain. But it's a simple circuit operation. This Hadamard gate and a quantum CNOT gate, you get an EPR pair. So there's a lot of very interesting physics around these sort of entangled circuits. Okay, entangled states. All right. Okay. The last gate we need before defining quantum circuits is none other than QNAND. Okay. So QNAND is basically a version of the NAND gate, but for the quantum world. Okay. And the quantum extension of NAND is a little bit weird, and I'll tell you why it has to be weird. So what's the definition of NAND? Right? So you take A and B. We saw this, a long time ago, but we don't have to remember too much. So not of AND A comma B. Okay, so this was an AND gate, right? So one important difference between classical gates and quantum gates is any quantum circuit or any quantum gate has to be linear, and at the same time, because it preserves length, is always a bijective mapping. Okay, must be invertible. Meaning, if I give some inputs, two different inputs can never collide under a quantum circuit. Okay, and the gate, it's also true for a gate. Gate is just a simpler circuit. Okay, again, this is a very different thing from classical computing. NAND itself, whenever we implement it, it is destructive in the sense that I can have two different inputs going to the same output. Okay, so for example, 0 and 0 go to 1, right? So NAND of 0, 0 goes to 1. Let me write this as a vector. Okay, maybe not as a vector, it might get confusing. NAND of 1 comma 0 equals 1. Okay, have two different inputs going to the same output, right? But this is not allowed under the laws of quantum mechanics. Every gate, every transformation that you build has to be linear and must preserve length. In particular, it must be invertible. Okay, so quantum computing is by definition reversible. If you go from input to the output, from the output you should get the inputs. Okay, makes sense? So how do I define a version of NAND for the quantum world then? There are various tricks around this, but the most prominent one that is used for almost any extending any classical function or classical definition that you have to the quantum world is to introduce an extra bookkeeping register. Okay, which is kind of what the control NOT did. So let me elaborate on that. So instead of looking at a NAND as taking 2 bits and outputting single bit, I'm going to introduce a NAND prime, okay, which takes 3 bits, A, B, C. Okay, think of C as just like a placeholder, which is used to store the value of the NAND. All right. So this is NAND prime. I'm just going to put this symbol here. I'm making up the symbol, so if you see something else somewhere else, maybe let me say and here. Okay. So NAND prime effectively just does A and B here, all right? But on the last bit, it stores the value of the NAND. Okay? So this operation, which takes 3 bits and outputs 3 bits, is effectively giving me the value of the NAND of A and B. Right? If I know C, I can always decode it, but it is an invertible transformation. I cannot have two different sets of inputs which will collide. Yeah? Not necessarily. It's just, there is a mapping from the output to the input. Okay? In some cases, it is the same. Like for the Hadamard gate, it's the same, but not for all. Okay? And for the NAND also, it's the same, but it need not be universally true. Okay? Good question. Any other questions? It is a bit weird why we are having to do this kind of, make things more complicated. But the reason we have to make things more complicated is because of the restrictions from quantum mechanical laws. Okay? So if you're thinking of extending classical gates, classical functions to the quantum world, you typically use this trick where you have an auxiliary sort of register or qubit, which is supposed to store the value of the gate or function. Okay? So this is kind of, the punchline here is that this is a reversible form of NAND. Okay? Still classical, but it's a reversible form of the NAND gate. Okay? And just as an aside, back in the 80s and 90s, people were, even before quantum computing became a thing, people were studying these kinds of reversible formulations of all gates. And they had a very, very interesting sort of theory behind it. And one of those theories was that reversible computing can be more energy efficient than usual computing. Theoretically speaking, implementing just a standard NAND gate must lose some energy because of loss of thermodynamics. It's destroying information, so anything that you build, any physical device which implements a NAND gate must lose some energy. Okay? Whereas if it's a reversible computation, then you're not violating laws of thermodynamics. You can get much more efficient versions of reversible gates. There was this whole field of reversible computing where they wanted to design kind of, take any circuit, I'm going to make it a reversible circuit, and that would require less energy to run. But at some point, the cost of the energy was so low that it just died. Okay? So making things a bit more complicated, but more energy efficient, but the complication kind of, was too much to make, the win from preserving the energy was not enough. Okay, but it's a beautiful theory that because of second law of thermodynamics, a NAND gate, any implementation of NAND must lose some energy, whereas of the reversible NAND, you can potentially get a much more efficient version. Right? That's an aside. Okay, so now we have this NAND prime. So this is what we are going to use to define our quantum NAND gates. Okay. Is the quantum version of NAND prime. Okay, meaning so my gate is going to take 3 qubits okay, and output 3 qubits. What is this gate supposed to do? Well, I'm going to tell you what it does on the basis states, and then we can use linearity to extend it to all possible superpositions. Okay? So for example, if I send in 0, 0, 0, I should get 0, 0, 1. You can check this, right? So NAND prime, the first 2 bits always go through as they are. The last one gets XORed with the NAND operation. Okay? So that's basically it. So if I have 1, 0, 0, that goes through as 1, 0, 1. If I have 0, 1, 0, then I should get 0, 1, 1. 1, 1, 0 goes through as 1, 1, 0. Okay? So if you have a 3-bit system, you are in 8 dimensions. So you need to specify what happens for each of the 8 basis vectors. Only then is your description complete. Okay, so this is 4. I'm going to be lazy and do it this way. Okay. So this is what the quantum NAND is supposed to do. This is the operation on the basis states, and hence we know exactly what it's supposed to do on all of the superpositions. Okay. Any questions so far? All right. So now we are in a position to define quantum circuits. Okay. And before we go there, let's recall how we defined classical circuits. We had this notion of NMS NAND circuits, right? So an NMS NAND circuit had n variables, which we said were, x0, x1, all the way up to xn minus 1. And then you had S gates. Okay. And then, some variable names. And this was y1, maybe this was y2, and so on. Okay. So a NAND circuit was basically a directed acyclic graph which had S nodes in it and so on and so forth. Okay. So the definition of quantum circuits is very similar. In fact, at this point, I think you can take a guess. We replace NAND gates with, any guesses? What should we replace them with? No mystery here. We just replace NAND gates with QNAND. Okay. But this by itself is not enough. For when we talked about circuits, whether you had AND or NOT operations or just NAND operations or something else, they were all equivalent to each other. Okay. To get kind of the same thing, it's not enough to just have Q NAND gates. You also need one other gate, and that's the Hadamard gate. Okay. So that's what a quantum circuit is. You basically take the usual definition of a circuit, but instead of NAND gates, you're now allowed to use Q NAND gates and Hadamard gates. So Hadamard and Q NAND are complete for computing all possible quantum circuits. Okay, we're not going to prove that. It's much trickier to do this in the quantum world, but we can at least define it this way. So let me draw a picture, and then just as we did for the Boolean thing, for the classical case long time ago, the actual definition will be a little bit messy, but that's fine. Okay. So for a quantum circuit, just as before, you will have n inputs, but the inputs are now photons. Okay. So imagine I initialize my photons corresponding to whatever input on which you're doing the computation on, right? So the circuit is quantum, but the inputs are still classical. I'm trying to compute something like, let's say I want to compute majority of X for whatever reason. That's a trivial thing. We could have done it classically, so it's not as interesting an example. But that's all there is. And I'm trying to compute an usual function just as we did before, but the circuit is quantum. Okay. And the way we load up the input is by having n photons. Okay. And the initial state of each of the photons corresponds to the input bit that we have. Okay. But this is not enough. Because of the laws of quantum computing, which tell us that we cannot destroy information, okay, we have to allow some extra photons basically as memory. Okay. So in the definition of quantum circuits, you have the n input bits, and then you have a few ancillars. I don't know why they're called ancillars, but that's the name that somehow that's stuck. Okay. And you can assume that all of these photons are just initialized to 0. Okay. So you have extra registers or photons which are meant to store, intermediate things. And then you just have the usual diagram. I might send these 3 through a quantum NAND gate, and then maybe the first one through a Hadamard gate, and so on and so on. Okay. Maybe there's another Hadamard gate here, there's another Hadamard gate here, and so on. Okay. So the gates are still operating kind of locally, in the sense that at a time a QNAND can operate on at most 3 qubits, right? 3 photons. My Hadamard gate operates only on 1 qubit, right? And eventually you get the same photons out in potentially a very messy superposition. We have no control, at least from the description, on what happens to the final state. Okay. And just for simplicity, I'm only going to define quantum circuits where you only output a single bit. Defining multi-qubit, multiple output things is a bit trickier. You need to take care of entanglement and partial measurements and so on, which is, important, but a little bit messier. Okay. So this is what my quantum circuit is going to be. So the inputs are loaded up into the first n photons. Then I have some number of ancillars or auxiliary photons. I run all of them through my obstacle course of QNANDs, Hadamards, and so on. And then I measure the first photon in the HV basis. Okay. If I get a 0, I'll say the output of the function is 0. If I get a 1, I'll say the output of the function is 1. Okay, that's my guess for it. Any questions about this definition? At least the picture. We'll formally define it. It will be more tedious when we define it formally. Yeah? The QNANDs have 3 inputs each, right? But like imagine, let's say my input was only 2 bits. Okay, then I need an extra thing even to define the QNAND. Okay, so the ancillas are actually important not just because of the QNANDs. They might be important for kind of getting, storing intermediate values. You can think of it that way. Okay, you can never destroy information. There's something called the no cloning theorem, which is also a quantum phenomena. You cannot copy a variable at all. There's sort of some weird things that happen, and the model definitely changes if you limit the number of ancillas. Okay, so you have to allow ancillas to get meaningful quantum computation. Yeah, it does. So at the end of I do all of these things, and it's kind of weird, but I'm only looking at one particular photon. Right? It's kind of like what we did in the circuits too, right? You process the circuits, all of the intermediate wires are carrying values, but for the output, I only look at one particular wire. Okay, so once I do this measurement, all bets are off, right? So I'm destroying information, and then I get a value, I get an output value. Okay, so until the measurement, this entire box, what it does is invertible. Okay, every one of these things, if you know the output, you know the input, right? So the entire circuit is 1-to-1 until the measurement. Okay, you can also define a version where you allow measurements in between. In fact, when you start talking about quantum algorithms, you have to allow that so that things make sense. But you can always push all of the measurements to the end. It doesn't change the underlying model, but makes the physics much easier to picture. Okay, so I build this obstacle course of my original photons and some ancillas, and then in the end, I measure the first photon. Okay. Any other questions? All right. So to make this sort of ultra concrete, we can say a quantum circuit on QNAND, Hadamard gates, okay, on n plus a qubits. So n is the number of inputs, a is working memory or ancillas. Okay, is a sequence of gates. All right. And the other thing that we should draw differently from quantum and the classical circuits is in the classical world, the time ordering didn't quite matter. Okay. It's a DAG, so it was fine. In the quantum world, it's even more important to keep track of time in some sense. Okay. So always imagine that the gates are sort of happening one after the other. Okay. That's a good picture to have in mind. Even if the gates are operating on completely different inputs, just imagine applying the first gate and then the second gate. Okay. Just because one is only operating on the first bit and one is only operating on the last bit doesn't mean that I can put them two at the same time. Okay, that can lead to some weirdness because of superpositions and so on. So you should put them one after the other. Okay. All right. So definitions wise, if you're careful like this, things are pretty simple. Is a sequence of gates. I have n plus a qubits, and I have a sequence of gates now. So gate 1 is, then I have gate 2, so on up to gate S. And each gate is a QNAND or a Hadamard gate. Okay. And in terms of description, if it's a QNAND, I need to tell you what are the 3 photons indices that I'm operating on. If it's a Hadamard, I need to tell you which photon am I operating on. Okay. So the description of a quantum circuit is now simple. I tell you, okay, gate 1 is QNAND 135. Gate 2 is Hadamard 7. Gate 3 is QNAND 257 or something like that. Okay. So once I have the sequence of lines, that's exactly what a quantum circuit is. Simple to describe, but we cannot anticipate the output. We cannot compute the output classically without an exponential blowup. Okay? All right. So that's what the model is. Now, how does it define computation? Okay. And we say a function is computed by a quantum circuit as above if for every input x, if the input photons are initialized as x0, x1, all the way up to xn minus 1, and the ancillars are initialized as 0, 0, 0. The 0 is arbitrary. We just need to fix something. So we'll just pick 0. Okay. And I measure the first photon under a HV device. Okay. The probability output of measurement equals f of x is at least 0.9. Okay. So this is the other anomaly from classical circuits, in that for classical circuits, once you give an input, the output is determined. Whatever it is, if the input is something, I'll get a 0 or a 1, and the output never changes. Okay. But quantum circuit, and especially because of the measurement at the very end, it's a randomized process. Right? Sometimes I might get a 0, sometimes I might get a 1. Okay. But we are happy as long as the probability that my measurement gives the right answer is at least 0.9. Why 0.9? It's not that important. I can boost this probability as much as I want by repeating the experiment. So let's just fix a constant, which is 0.9. Anything more than a half is good. Yeah? That deterministic until the HV. Until the HV, yeah. Right, so until then it's invertible even, right? So there's just almost no ambiguity. Of course, we cannot compute it, but once I do the measurement, I might have introduced some randomness. Okay. Any questions about the definition of what a quantum circuit is and what it means to compute a function by a quantum circuit? Okay. Yeah. The first photon. Remember, these are photons, right? So the photons went through my obstacle course. All of them came out, right? There is a specific notion of a first photon. The states are changing, but the object is still there. I'm measuring that device, that photon. Okay. Again, measuring the first one versus measuring the nth one, all of that is arbitrary. We're just fixing some convention. Okay. Yeah. 0 is encoded as 0 basis. Good point. I should stress that. So basically, if the measurement is the 0, like the horizontal polarization, I'll guess that the function's value is 0. If it's vertical, I'll say the function's value is 1. Okay. Again, that's just a convention, and that's fine enough. Okay. So now we have a model of quantum circuits, and more importantly, we also know or kind of have a notion of being computed by a quantum circuit. Okay? So if a quantum circuit, we'll say it computes a function f if for every x, the chance that I get the right answer is 0.9. Okay? So remember that the guarantee is for every input x, I need to have very high or pretty high confidence of getting the right value. Okay? All right. So what can we do with this quantum circuits? Why go through all of these hoops, etc., to define a new model? People had some good applications. One of the most important applications was quantum chemistry. Basically, any chemical reaction, especially in the quantum world, if you're using quantum laws, you can map it to a quantum circuit. Okay, you can prove that. A system with n particles, depending on the molecules or whatever you have, you can map it to a system with a comparable number of photons and comparable number of gates. Okay, so if I can build quantum computers, then I can, just simulate any quantum system reasonably efficiently. Okay, that was the first application. But for us as computer scientists, the real shot in the arm for quantum computing came due to an algorithm by Peter Shor in 1992. Okay, so in 1992, it was around the same time that not too long after public key encryption was invented. Public key encryption, of course, is really fundamental to everything that we do today, to all of e-commerce and so on. Okay, and all of those, even to this day, more or less, many systems rely on the following problem: not having a good algorithm. Okay, it's kind of a weird thing to say that I get all of these algorithmic sort of implications. I can run digital transactions securely. I can send emails in an encrypted way. I can have Bitcoin. I can have, I can buy stuff on Amazon without fearing that somebody will steal my data, because we assume the following problem does not have an efficient algorithm. Okay, and what is that problem? So that's the factoring problem. Okay, and because I'm talking about circuits, I'm just going to define it if it's fixed number of bits. Okay, and factoring of n should give me, let's say, a comma b, such that a times b equals n, a is not equal to 1. Oops. Okay, so it's a function which maybe, okay, so let's say, let me put, okay, so let's say 0, 0. Okay, so it views the x, this should be x, sorry. Okay, so it views the input string as a number in binary notation. Okay, so I'm giving you the number in binary notation, and if it's a prime, just give me 0, 0. If it is not a prime, you have to give me two numbers such that a times b equals x, and neither of them is 1. If you just ask me for a times b equals x, it's very easy. I would just give you 1 comma x, right? So to avoid that cheat, or x comma 1, I'm saying you have to, if it is not a prime, in which case there exists such a representation, you have to give me one such factorization. Okay? So simple enough problem to state. For example, again, it's a little bit underspecified because there can be multiple right answers here. Okay? But you can make it as a search problem and so on. So let's not worry too much about it. But the point is, I want to give you, like if I give you something like 1, 0, I have to give you two possible things where the product equals that number in binary notation. Any questions about the definition of the problem? Okay. Strange problem to study, but as I said, it's one of the most important problems economically. If you find an algorithm which solves this, you can basically break every possible digital transaction in the world. Okay. And much of it relies on assuming that this problem is hard to solve. The best algorithm runs in time something like 2 to the n to the 1/3 or 1/5, I forget, some exponent. Okay, kind of better than brute force, but still quite bad. So even if n is like 1,000, you're running very, very slowly. Okay. Now, Shor in 1992 showed that there exists a O of n squared size quantum circuit. To factor n bit numbers. Okay, so for this problem, there is a quantum circuit which only needs n squared gates. That has also been improved since then, but Shor's original thing was n squared gates, quadratic runtime, more or less. Right? Because each gate is like one unit operation. We usually think of a gate like an AND as one unit operation. Okay? In the quantum world, is saying there is a quantum circuit with n squared QNANDs and Hadamards, which can factor a number. Okay, and this was a big surprise to many people, and kind of really showed the importance and power of quantum computers. If I can build a quantum computer, then factoring is broken, and hence most of our encryptions would be broken. Okay, and it's not just like they're broken for the future. If you build something in the let's say I build in year 2080, I build a powerful quantum computer, I can go back and potentially decode many encrypted messages. Because they're all encrypted, using factoring as a hard problem, I can break all of them. Okay, said this was like a staggering surprise, and really force people to rethink quantum computation, not just as a curiosity, as something that would be useful for chemistry, but also very fundamental for algorithmic tasks. Okay, any questions about the statement of this result? We're not going to do the proof of it, but if you're interested, there's some other classes that our department offers which go into it. Okay. All right, it involves like Fourier transforms and lots of really beautiful math behind it. All right. And because of this, for example, now there's a large push towards building encryption schemes or signature schemes or doing digital transactions in what is called post-quantum crypto. So trying to build things which would be secure even if, let's say tomorrow somebody comes up with a quantum computer. Okay. Anyway, that's a whole new research area. It's not just something that's 5 years old. It's current technology. All right. Okay. So that's one example of a sort of a quantum advantage, probably the most important quantum advantage that we can have. If you have quantum circuits, I can get exponential speed up over for this particular problem. Okay. And then there are all kinds of myths about quantum computing. Okay. So the first myth, which is based on some fact, is that if I have an n-qubit system, okay, if I have an n-qubit system that has 2 to the n basis states, right? So this is basically something like alpha x times x. X is a string in 0, 1 to the n. Okay. Now you can now imagine if I have a quantum circuit C, then C is a quantum circuit. The action of the circuit here would satisfy linearity again. Okay, until the measurement. Let's say we don't do the measurement, we're talking just about the circuit itself. Okay, so this would just be okay. So it seems like a single application of the quantum circuit can mysteriously apply the kind of the circuit on all possible input strings that I care about. Okay, it's kind of hidden in the final state, but as I said earlier, the fact that the state has all of this information doesn't mean you can access it. You have to pay a penalty to access it. If I compute, for example, if I try and extract out the value of, let's say, what happens on 0, 0, 0, it will destroy the state. Okay, so it is this interference that means that I'm just not applying things in parallel and then I can read all of them at once. That is not possible. Okay, when I read a single output, it might change the entire circuit, entire state, and we don't know what is going to happen. Okay, so even though the circuit is behaving as if it's computing all of these CXs in parallel, it's not like you can access them. They're there in my state, and there are these weird rules on what kind of information I can learn about them from the state. Okay. All right. And in this vein, let me tell you about one other really beautiful algorithmic thought experiment that is due to Deutsch and Joseph. Okay. Now, they said consider the following toy problem. I have some function, okay, which takes n bits and outputs a single bit. All right. And I'll tell you how we are given access to this function in a second. But for now, we're just given this function. And what are we doing with it? I want to detect the following cases. F is a constant function. or F is perfectly balanced. Meaning on half the inputs, F is 0. On half the inputs, F is 1. Okay? So imagine that somebody gives you a black box access to this function. The function is sitting in the sky. It has, it is in one of these two cases. It is either a completely constant function or it is perfectly balanced. On half the inputs is 0, half the inputs it is 1. Okay? And our goal is to kind of keep querying this black box and figure out which case we are in. And let's say every time you press the button to ask the box, you get charged $1. Okay, and the question is how much do you need to spend to compute which case you're in? Any guesses? In the classical world, what can happen? How many guesses, how many times do I need to go ask this box, this black box in the sky for various inputs? Like, for example, I'll say, okay, here's my first input. 0, 0, 0. I get back f of 0, 0, 0, right? And then maybe based on that, I decide, okay, ask it on, maybe 1, 0, 1, 0, 0, 1. I get some answer, and so on and so forth. Okay? So every time I go up to the box and ask for a specific value, I'm paying a cost. Okay? So in this world, how much, what do you think is the minimum possible cost to distinguish between these two cases? Any guesses? Let's take a heuristic guess. Let's forget about proving, but what would be the least possible? Any guesses? Yeah? Right. So you're right, except quantitative, it's not n over 2, it's 2 to the n. Right? There are 2 to the n inputs. There are n bits, so the number of inputs is 2 to the n. Okay? So pretty much until I query half of the inputs, I don't know which case I'm in. Right? All of those could be 0. That doesn't mean the function is constant or balanced. Until I query more than a half, I don't know the answer. Okay? So in fact, you can prove this classically. You need to query or pay 2 to the n minus 1 plus 1. Okay. So you have to query the box at least 2 to the n minus 1 plus 1 times to figure out the answer. Okay? Makes sense? Now, until I see all of these things, I don't know. If I only see half, all of those could be 0, but it doesn't tell me which of these two cases I'm in. It could be a constant function, or it could be perfectly balanced. I wouldn't know until I query at least one more bit, one more input. Okay? Now, what did Deutsch and Jossa do? They said, imagine instead of this, I have kind of a very similar thing, but a quantum access to F. Okay, so I have a quantum circuit. or quantum box that computes F. Okay. And once again, because of this annoying thing that, not annoying, but kind of, important but seemingly annoying property that quantum devices cannot destroy information, you can think of it as I give it X as input and some ancilla, which is 0. Okay. And I get back X and f of X here. So let's say I put a here. If I put a 1, I get that. Okay. Kind of how we encoded NAND operation as a quantum operation so that it is realizable, right? So we said we have an ancilla, an extra register, which kind of really stores the value of the output of the NAND. Okay. In the same way, I'm giving you access to a box, which is a quantum implementation of F. Give me X and some ancilla A, the X goes straight through, and the output of F is stored on the last register. Okay. Any questions about this? It's like the classical analog, it's the quantum analog of NAND, but the same thing done for this potentially more complicated function F. All right. And here, this is really surprising, but it doesn't have any practical applications, but remarkable nevertheless. Forget the year, I think again 90s, or maybe even earlier. Let me see. What year was this? I think 80s. Okay. So what they showed is we can figure out which case we are in with probability 1. No chance for error. Okay. So it said if it is quantum, I can actually figure out which case I am in, whether half the inputs are zeros and half the inputs are 1, or all of them are zeros, by making one use of the box. Okay. It's super counterintuitive, but it's kind of encoded in how quantum mechanical laws behave. Okay. So if I'm giving classical access, there's nothing beyond making half the number of queries. Whereas in the quantum world, I can basically do it with one query to the box. I have to do some other computation afterward, but the box itself, I would only press the button once. Okay. So there are lots of, there are several such examples where you get significant quantum advantage. There's something called Grover's search algorithm, where once again you get a speed up in the quantum world compared to the classical world. Okay. So these are some of the reasons why we really care about quantum circuits. And as I said, we have a complete description of being computable by a quantum circuit now. Right? And the current experimental status is really about, we need to be able to realize these kinds of diagrams physically. Okay. And there's some progress on it. It's always debated. Somebody says I did it. Some startup says I did it on 100 qubits. And then someone else says, okay, no, you are just cheating. There's something classical hiding behind it, and so on and so forth. Okay. All right. So this is kind of the big picture behind quantum and why do we care about it. Let me finish by sort of like a silly, maybe toy problem. Okay. And this is the following. To gain some intuition for how to design quantum circuits. Okay. So IBM actually has a website where you can code up. Okay, so they have their own sort of language for describing quantum circuits. And then they have a simulator which tells you the answer on specific inputs. And as I said, it's not easy to compute the expected answer of a quantum circuit on a classical computer. That's the whole point. But they can do it for some small inputs. Okay? So for now, let's try and do the following transformation. Okay. I want a quantum circuit, which, again, as I said, there's no practical application of this except for us gaining some understanding of quantum circuits, how they behave, and how you would go ahead and design circuits later on. Okay. So let's say my goal is I get a 3-qubit system, which is in the state 0, 0, 1. And my end goal is to get this state. Okay. And I want you to design a quantum circuit which does this. All right, so I send in these 3 photons. If the input state was 0, 0, 1, what I should get as output should be that state. Okay? So if I ask you to do such a thing, the only gates that we have are CNOT, QNAND, and Hadamard. You can also use NOT if you want, but I think for this one, all you need is just Hadamard and CNOT. Any suggestions on how you might get started, how to do this transformation? Well, the first thing is I need to apply the Hadamard somewhere, right? You can start guessing that I need to use the Hadamard somewhere because I'm kind of, that's the only one which can create superpositions if you don't already have one, right? C naught of 0, 0, 1 will just still be without any complicated superposition, right? Hadamard is the only one which can kind of split things, right? So, let me just take a wild guess and apply Hadamard on the first photon. Okay. If I do that, so this is my state at the beginning. What's my state here? So I'm applying the Hadamard on the first qubit. So that qubit becomes 1 over square root 2 times 0, right? And 1 over square root 2 times 1. The remaining 2 are not changing, right? So I would just get 0, 0, 1, 1, 0, 1. Okay. So I made some progress. But I have 4 things involved in my superposition here, each one with a factor of a half. Now I have 2 things with the 1 over square root 2. So what should the next one be? Any suggestions? We should do Hadamard again somewhere, right? So because we need to split further, and there's no way around that. If I just use C naught, it's only going to map basis states to basis states. It's not going to create new superpositions. Okay, so you can do Hadamard on second or third as well. I'm going to do on the third one, and I'll tell you why in a second. I'm doing the Hadamard on the third one because just to make things simpler, the third one is just state 1 in both cases. Okay? So what happens then? Well, I need to compute what happens. And how do I do that? I would use linearity. Okay? So what would the Hadamard do on this state and this state separately, and then put the 2 together? Okay? So if I apply the Hadamard gate on this, I would get 1 over square root 2 times h of, or let me write it as h on third qubit of 0, 0, 1 plus 1 over square root 2 times h on third qubit of 1, 0, 1. Okay? And the third bit is a 1, so the Hadamard gate creates 1 over square root 2. The first 2 don't change, and the last one splits into okay. So Hadamard on 1 goes to the minus position, right? So which is 1 over square root 2 times 0 minus 1 over square root 2 times 1, and then I get the same thing, which is here 1, 0, 1 minus, sorry, this is a 0, 1, 0, 1. Okay. This seems somewhat tedious, but as again, there's no way around using linearity and doing these calculations if you want to find out what happens to quantum circuits. If you want to design quantum circuits, you have to do such calculations. Okay? So we got lemons, we are making lemonade. Okay, so and as I said, Hadamard is kind of probably the most important quantum gate. If I don't have it, if I just have Q nans, you get no power really, because basis states will only go to basis states. Hadamard is the one which kind of mixes things. Okay? So, you should really appreciate the Hadamard gate and try and use it if, when you need to. Okay? So now we are almost, kind of making some progress in that our end desired state had 4 things. I also have 4 things. Not all are matching, so I need to adjust them. But I can, okay, let me write down my target so that we know what we're doing. Okay, so this is our target. Okay, so in some sense, we made significant progress. Like, this one and this one match, this one and this one match, but these 2 don't match. Okay. So what do I do now? And now you kind of do a case analysis to see, okay, What happens if I use CNOT gate on the first bit? What happens if I do a CNOT gate on the second bit, and so on and so forth? Okay? Does it make sense? So you're trying to guess the sequence of gates one step at a time. The first observation was we need to use the Hadamard because I need to create a more complicated superposition. If I did only one, I got superposition of two basis states. But my target had four things. So I created another Hadamard gate that gave me four things. Now I'm almost matching up, right? So I got two of the basis states exactly as I wanted, but two are off. Okay? And then there are various ways of doing it. I'm not going to do that computation, but you just do a trial and error of what CNOT gates to use, or at least I don't want to use any more Hadamard gates because that's going to introduce more 1 over root 2s, which would destroy the progress that I made. So I want to stick to CNOT or QNAND kind of gates. Okay? And if you play around for a few minutes, this kind of works. If I do CNOT here, and then CNOT here. Okay? And you can check that this exactly does what we want. So check. All right. Yeah.
I thought when we were working with photons, we had to use QC0.
Right. QC0. Sorry. Yes. QC0. Yeah. This is QC0 for sure. Yeah. So this is QC0 with the first one as a control bit, the third one as a control bit, and so on. Okay. But there are many different ways of doing it. You can also, I'm sure if people will come up with like ways with using QNAND if you want, or maybe doing CNOTs in another order and things like that. But there are the steps in guessing how to get there, which is, okay, I need to create more complicated superpositions, so I do Hadamard. How many Hadamards? You kind of make a guess, and then you try and massage the states one after the other. Okay? And if you're really interested in this stuff, as I said, IBM has a website where you can play around with this, and you can give it input. Like, I give the circuit, I specify it, and I say, tell me what's the answer, what's the output when I give 0, 0, 1 as the input. Okay, it'll give you the answer, kind of compute it directly and tell you the answer. Okay, we don't need that because we're working only with small things, but this is just to gain some intuition for how to compute with quantum circuits. The biggest anomalies, as I said, are linearity. Okay, it's a weird thing that nature respects linearity. Everything is linear. It kind of ties our hands a little bit, but we are still able to make very non-trivial computation with it. Okay, so that's all I wanted to say about quantum circuits. And so there is, given the progression that we went through at the beginning, right? So we said circuits are nice, you can implement them in the physical world, but then they had these limitations, which we overcame by going through DFAs, NFAs, and Turing machines. Okay, you can do the same progression for quantum as well. Okay, quantum circuits are great because it's a very concrete definition. We only have, there is QNAND, but I should say like the quantum thing comes from the Hadamard gate. Okay, it's the most important gate. And you have circuits, you can then define quantum DFAs, you can define quantum NFAs, you can also define quantum Turing machines, kind of the same progression. Okay, but given the classical stuff that we did, you don't have to reinvent the wheel. Okay, you can take some shortcuts, for example. The way you define, this is not needed for us, but just to kind of give a spoiler, the way you define quantum Turing machines is to say, I just need a Turing machine, classical, like our usual Turing machine, which writes down the description of a quantum circuit. Okay, so you save some time by not having to reinvent and redefine everything, but using our classical notions and just mixing it with the quantum stuff. Okay. So that's all I wanted to say. And I have office hours today from 4 to 5, but if not, I'll see you on the exam on Tuesday. The question? Yeah?
For the first part, I think we split it with like addition, but then the second one, it with subtraction.
Good question. So that was because the second Hadamard, when we are applying it, we are applying it on the 1, the third bit, right? So Hadamard on 0 is 1 over square root 2 times 0 plus 1 over square root 2 times 1. Hadamard on 1 is 0 minus 1 over square root 2 times 1. Okay, so that's why. And the number of minuses can also give you an indication as to what Hadamard to apply. Okay? All right. So good luck with the exam, and I'll see you hopefully on Tuesday. Okay? All right.
Yeah. I have a quick question about
Yeah.
homework.